Today we are going to learn functions. If A and B are two sets, then the Cartesian product denoted by A cross B is defined as A cross B is equal to set of ordered pairs xy such that x belongs to A and y belongs to B. Set of ordered pair AB, where A belongs to capital A and B belongs to capital B. A function f from A to B is subset of Cartesian product A cross B. Cartesian product A cross B. A function f from A to B is called one-one function, one-to-one function or one-one function. If fx is equal to fy implies x is equal to y for all xy belongs to A. This definition is also written as contrapositive of above statement, that is, x is not equal to y implies fx is not equal to fy. Then f is said to be one-to-one function. F from A to B is a function. The set capital A is called domain set, and capital B, the set capital B is called codomain of the function. F of A, f operates on A for all A belongs to capital A is called range set of the function. Range set of the function f is equal to codomain, then function is said to be onto function. Onto function. If the range set is subset of codomain, that is f of A is subset of f of B, then f is said to be into function. For example, if f is function from capital N into N, where capital N is equal to I, that is set of positive integers 1, 2, 3, 4 and so on up to infinity. And fx is equal to 2x for all x belongs to N. This function is into function. Since f of x, that is range set of this function, is equal to 2, 4, 6 and so on. Range set is equal to 2, 4, 6 and so on, which is subset of set of natural number n or set of positive integer I. Therefore, this function is into function, not onto function. Onto function. So first we write definition of cross product, Cartesian product, cross product. Cartesian product, if A and B are two sets, capital A and B are two sets, then Cartesian product of two sets A and B is denoted by capital A cross B and is defined as A cross B is equal to set of ordered pair xy such that x belongs to capital A and y belongs to capital B. Definition. If capital A and capital B are two sets are sets. Then Cartesian product denoted by A cross B and is defined as A cross B is equal to set of all ordered pair XY. Set of ordered pair XY such that X belongs to capital A and Y belongs to capital B, such that X belongs to capital A and this Y belongs to capital B. Or you may write A cross B is equal to small a comma small b, such that A belongs to capital A and B belongs to capital B. This is the Cartesian product. For example, if A is equal to 1 and 2, B is equal to, set B is equal to small a, then A cross B is equal to ordered pairs 1A, 2A. This is Cartesian product A cross B. Next definition. Let A and B be any two sets, capital A and capital B be any two sets. A function F, from A to B, A into B is subset of A cross B, is subset of A cross B, or any subset of A cross B is called a function from A into B. A function F from A to B, another definition. A function F from A to B is said to be one-to-one function. Is said to be one-to-one function, or one-one function, if fx is equal to fy implies x is equal to y. Fx is equal to fy implies x is equal to y for all xy belongs to capital A. xy belongs to capital A. Or contrapositive of this definition, or x is not equal to y, implies fx is not equal to fy. For all xy belongs to capital A. xy belongs to capital A. Here the function Here the set capital A is called domain set and B is called codomain set. Codomain set. If f of A is equal to B, then the function is said to be onto. If f of A is equal to B, then function is said to be onto. Then function is said to be onto. Is said to be onto. Now we see some theorem. Here A is domain, B is codomain. If f is 1, 1 from A to B, 1, 1 and onto, then f inverse exists. Theorem number 1. Statement of theorem 1. Theorem 1. If f from A to B, f from capital A to B, and if x is subset of B, capital X is subset of B, capital Y is subset of again B, then f inverse of X union Y is equal to f inverse of X union f inverse of Y. F inverse of Y. Proof of this theorem. Since f is function from A into B, f is function from A to B, and capital X is subset of codomain, capital Y is also subset of codomain, then f inverse of X union Y is equal to f inverse of X union f inverse of Y. A is equal to B. The set capital A is said to be equal to B if A is subset of B and B is subset of A. B is subset of A. A equals B means A is subset of B and B is subset of A. If and only if A is equal to B. Suppose A belongs to f inverse of X union Y. X union Y. This implies f of A belongs to capital X union capital Y. A belongs to f inverse of LHS, f inverse of X union Y. This implies f of A belongs to X union Y. This implies f of A belongs to capital X, or f of A belongs to capital Y, belongs to the set capital Y. Capital Y. This implies A belongs to f inverse of X. A belongs to f inverse of capital X. or A belongs to F inverse of capital Y. This implies A belongs to F inverse of capital X union F inverse of capital Y. That is, A belongs to F inverse of X union Y implies A belongs to F inverse of X union F inverse of Y. Therefore, we write F inverse of X union Y. X union Y is subset of X union Y is subset of F inverse of X union F inverse of Y. F inverse of Y. This is say relation number 1. Conversely, suppose B belongs to F inverse of capital X union F inverse of Y. F inverse of Y. This implies B belongs to F inverse of X. F inverse of X. B belongs to F inverse of X, or B belongs to F inverse of capital Y. This implies F of B belongs to capital X, or F of B belongs to capital Y. Either F of B belongs to capital X or F of B belongs to capital Y. This implies F of B belongs to capital X union capital Y. Capital X union Y. This implies B belongs to F inverse of X union Y. B belongs to F inverse of F inverse of X union Y. Therefore, F inverse of capital X union F inverse of capital Y is subset of F inverse of capital X union capital Y. Capital X union Y. That is, the element from F inverse of X union F inverse of Y is in F inverse of X union Y. This is say 2. From 1 and 2, we write F inverse of capital X union capital Y is equal to F inverse of X union F inverse of Y. F inverse of Y. Hence the proof of the theorem 1. Hence the proof of theorem. Hence the proof of theorem. Now we see the theorem second. Theorem second. Statement of theorem second. Theorem second. If f from A to B, capital A to B, and if capital X is subset of B and capital X is subset of B, capital Y is subset of B, capital Y is subset of B, then f inverse of capital X intersection Y, f inverse of X intersection Y is equal to f inverse of capital X intersection f inverse of Y, f inverse of Y. Proof. Suppose A belongs to small a belongs to f inverse of capital X intersection capital Y, X intersection Y. This implies f of A belongs to capital X intersection capital Y. This implies f of A either belongs to capital X and f of A belongs to capital X and f of A belongs to capital Y. F of A belongs to capital X and f of A belongs to capital Y. This implies A belongs to f inverse of X, and A belongs to f inverse of capital Y. This implies A belongs to f inverse of capital X intersection f inverse of capital Y. This means that the element which belongs to f inverse of X intersection Y is the element of f inverse of X intersection f inverse of Y. Therefore, we write f inverse of capital X intersection capital Y is subset of f inverse of X intersection f inverse of capital Y. This is result number 1. Conversely, suppose B belongs to suppose small b belongs to f inverse of capital X intersection f inverse of Y, f inverse of Y. This implies B belongs to f inverse of X and B belongs to f inverse of capital X. This implies f of b belongs to set capital X and f of b belongs to capital Y, where X and Y, capital X and capital Y, are subsets of capital B, that is codomain set. This implies f of b belongs to capital X intersection capital Y. F of b belongs to X intersection Y. This implies b belongs to F inverse of X intersection Y. This shows that the element in the set F inverse of X intersection F inverse of Y is the element of F inverse of X intersection Y. Therefore, we write F inverse of X intersection F inverse of Y is subset of F inverse of X intersection Y. This is a second. From 1 and 2 we write, from 1 and 2 we write F inverse of capital X, F inverse of capital X intersection Y, F inverse of capital X intersection capital Y is equal to F inverse of X intersection F inverse of Y. Hence the proof of theorem second. Thank you for watching the video.